Welcome to video 9, 3.5, limits at infinity. So this section is going to look at end behavior of a function on an infinite interval, or when x is increasing or decreasing without bound. So remember, in pre-calc you would graph these functions here, and what would they look like? Well, they would typically have branches, and as it's approaching a certain value, the function would continue to increase or continue to decrease to positive or negative infinity. So what is the definition of limits at infinity? So if L is a real number, the statement of the limit as x approaches infinity of f of x equals L means that for each epsilon greater than 0, there exists some m greater than 0, such that the absolute value of f of x minus that L is less than that epsilon whenever x is greater than m, okay? Or the statement, the limit as x approaches negative infinity of f of x equals L, means that for each epsilon greater than 0, there exists some number n greater than 0, such that the absolute value of x minus L is less than epsilon whenever x is less than n. So the statement, the limit as x approaches negative infinity of f of x equals L, or as the limit as x approaches positive infinity of f of x equals L, means that the limit exists and the limit is equal to L. So if you take a look, then kind of getting into horizontal asymptotes, the line y equals L is a horizontal asymptote of the graph of f if the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches positive infinity of f of x equals L. So that's where we get those horizontal asymptotes from. Okay, so let's look at limits at infinity. So looking at this theorem, if r is a positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the r equals 0. Furthermore, if x to the r is defined when x is less than 0, then the limit as x approaches negative infinity of c over x to the r equals 0. Okay, so let's look at this. Let's look at some of these examples here where we're going to actually find the limit as x is approaching infinity. Okay, so if we were to do direct substitution at this point, okay, our numerator, and we would break it up, right? So the limit as x approaches infinity of our numerator would go to infinity, and the limit as x approaches infinity of our denominator would go to infinity. So this doesn't necessarily work. We need to manipulate this function here so that we can use direct substitution. So one method is we can divide everything by the highest degree of x. So when we do that, it's going to look like the following. We will have the limit as x approaches infinity of our numerator divided by x squared over our denominator divided by x squared. When everything is cleaned up, x to the 3/2 over x squared becomes 5 over x to the 1/2, and our denominator cleans up to be 4 plus 1 over x squared. Now if we use direct substitution, we have 5 over infinity all over 4 plus 1 over infinity. Well, 5 over infinity, 5 over a really big number just goes to 0. And 1 over a really big number also goes to 0. So we're left with 0 over 4, which in our case is just 0. Take a look at the next example. Find the limit as x approaches infinity of 5x to the 3/2 over 4x to the 3/2 plus 1. I want you to think about how you can manipulate it so you can then use direct substitution. So go ahead, give it a try, and come back. Okay, did you get 5/4? So what I did was, since the powers were identical, I again divided everything by the highest degree of x, which is x to the 3/2. So when we do that, we end up with 5 over 4 plus 1 over infinity, which again, 1 over infinity goes to 0, and when everything cleans up, it cleans up nicely to be 5/4. You can take a look at the graph on the right. We end up with a horizontal asymptote at y equals 5/4, and you can see our function is getting closer and closer and closer to that asymptote. Try this next example on your own. I want you to think about what you're going to divide everything by. If you choose the highest power, is that really going to work this time when you use direct substitution? Go ahead, give it a try, and let's check back. You should have seen that dividing everything by x to the 3/2 doesn't allow you to use direct substitution without making more manipulations. So the best bet here is to divide everything by x to the 1/2, or the square root of x. So when you do that, you clean up the function nicely to be 5x squared over 4 plus 1 over x to the 1/2. Now we can use direct substitution. We're going to get infinity in our numerator, and we're going to get 4 in our denominator. Well, infinity over 4 is still infinity. So we would say that this limit does not exist. Looking at the graph of this function to the right, you will see that it continues to reach infinity forever. So it is not bounded, and that's why the limit does not exist. Now we're going to get into sketching graphs of these functions. So what we have to do is we have to remind ourselves a little bit of what we learned in pre-calc. Okay, so if I want to graph this function, this rational function, all right, we want to then talk about extrema, intercepts, asymptotes, and symmetry, right? So the first thing we do is we go back to our pre-calc bank, right? And we know the first thing we have to do is clean up this function. So we factor everything we possibly can. In the numerator, we take out a 3. We can factor that denominator. We can factor the numerator further, and then we can cancel the 1 plus x and the x plus 1. So we get our cleaned up version to be 3 times 1 minus x over x minus 2. So then we have to talk about holes, intercepts, vertical asymptotes, the behavior along the vertical asymptote, and our horizontal asymptote. So remember, holes are found when factors cancel. So we have a factor of x plus 1 canceling, so I would set that equal to 0, and I have a hole when x equals -1. To figure out that y value, we simply plugged it in to the new cleaned up version, and we got y to be -2. And to find our intercepts, we just simply plug in when x is 0, we would get -3/2, and we would solve for when y equals 0, and we would get x to be 1. Our vertical asymptote is when our denominator equals 0, so our vertical asymptote is x equals 2. The behavior along that asymptote, I take a look at the power of that factor from my denominator, and since it's an odd power, I know my branches will be in opposite directions along x equals 2. Now, our horizontal asymptote, remember, we compare the degree of our numerator, which is 2, to the degree of our denominator, which is also 2. Since the degrees are the same, we look at our leading coefficient. Now remember, the leading coefficient of our numerator is -3. The leading coefficient of our denominator is 1. So we get y equals -3 over 1, or simply y equals -3. So that takes care of all the pre-calc issues or aspects of graphing these functions. Now we have to get into the calculus portion. So what part is our calculus? Well, calculus comes into play when we talk about our extrema, when we talk about concavity, and we talk about critical numbers and points of inflection. So now we're going to go to our calculus knowledge. Okay, so we're going to use our calculus to find any extrema and also talk about concavity. In order to do this, we need to take the first derivative and the second derivative. So remember that quotient rule, low d high minus high d low all over low low, or you might have another little song that you remember, but when you use that first derivative and that quotient rule, everything cleans up nicely to be 3 over x minus 2 quantity squared. So if we were to set this equal to 0, we wouldn't get an x value, but this is undefined when x equals 2. So we have a critical number at x equals 2. Okay, so we're going to kind of put that off to the side. Now we need our second derivative. So again, we're taking the derivative of y prime, and we're using our quotient rule, low d high minus high d low all over low low. And when everything is cleaned up, we end up with -6 over x minus 2 cubed. So again, in order to find our possible points of inflection, we either set this equal to 0 or it's when the function is not defined. So in our case, we get a possible point of inflection at x equals 2. So what does this mean? So now what we're going to do is we're going to use the first derivative test and our concavity test so that we can learn more about what this rational function looks like. So if we take a look, and thankfully our critical number and our possible point of inflection is the same, so this is going to make it relatively easy. So I talk about what y prime is, the value. I'm going to talk about what y double prime is, and I'm going to talk about what's happening to our function relative to y prime and y double prime. So on the interval from negative infinity to 2, y prime is positive, and also from 2 to positive infinity, y prime is positive. So what does that tell us about y? It tells us y is increasing on both of those intervals, okay? Y double prime from negative infinity to 2 is positive, and from 2 to infinity is negative. So when y double prime is positive, remember y is going to be concave up. When y double prime is negative, y is going to be concave down. So we're going to use this aspect to help us graph the function. So what conclusions can we make from all of this? Well, by the first derivative test, we can go ahead and say that there's no relative extreme at x equals 2 because we don't have any sign change of y prime. Y is constantly increasing on both of those intervals, not constantly. By the concavity test, that's looking at y double prime, we know that we have a point of inflection at x equals 2 because y double prime changes sign. It goes from positive to negative. So y goes from concave up to concave down at x equals 2. So what I want you to do right now is I want you to try graphing this rational function on the graph and then come back and check how you did. Okay, so take a look. Don't forget, we had to graph all of the pre-calc knowledge. So we've got a hole, we've got a y-intercept, we've got our x-intercept. We know from the calculus portion that on the interval from negative infinity to 2, we're going to be concave up and increasing, which we are. Then, using a point of symmetry, I could plot the point 3, negative 6. Okay, so that's going to be used using our point of symmetry with our x-intercept. Okay, then using our calculus knowledge, I know that our function is going to be increasing from 2 to infinity. Okay, y is increasing, and we also know that we are going to be concave down. So here we have it, the other branch. Okay, so now we're putting everything together, our pre-calculus knowledge, and we're taking that extra step to talk about extrema and concavity and points of inflection. If you have questions, bring them to class and we'll discuss.